What's up, everybody, and welcome to this overview, refresher, or if you're with us for the first time, maybe you're a new tech in training, welcome. This is electrical safety for HVAC technicians, but it definitely applies to anybody working around electricity. If you're joining us today in the live, I thank you for coming in today. It's a Saturday morning in the middle of Illinois where I'm at. It is cold and gloomy and 36 degrees. It is a great afternoon for a nap. So I appreciate you coming in and joining me once again and, focusing on our learning. One of the biggest things and greatest things we can do to strengthen ourselves as a technician is to continue our learning. And sometimes that's going over the fundamentals and revisiting the things that we already know. So if you're a seasoned technician with us today, again, thank you and welcome. And especially to the seasoned technicians. If you've been in this, a year, 2 years, 5 years, 100 years, appreciate your feedback, appreciate your points of view and thoughts. If there's anything I can add or take away from this lesson, feel free to let me know. Today's lesson is based on Chapter 30 from the Fundamentals of HVACR by Carter Stanfield and David Scaves. It is from the fourth edition, particularly, but it's important that we understand electricity and what we're working with. One of the worst things we can do is to put ourselves in a position where we're working with things that we don't understand. Thing is, you know, part of what fear is a lack of understanding about a thing. The thing I've learned about electricity is that, if you really understand it, now nobody masters it. You don't, nobody's fully got it mastered. The more you learn about it, the more questions you have. But the more you understand a thing, whether it be electricity or whatever, the less you fear it and the less afraid you are, the higher probability of success, the less the likelihood of injury, or your bottom line is if you don't understand what you're doing, you really run the risk of getting hurt. So I always, when I taught this particular lesson in trade school, I would always just start with this thought, and I want everybody here today to always remember one thing, okay? And just as I said, we never really master electricity. Electricity is one of those things that we can try our best to understand it, to learn more about it, to learn how it functions. And then when we understand that, we can learn to function within its rules. Electricity can be very useful, and it can also be completely safe to work around if you stay within its rules, its parameters, and its limits. Um, if you don't follow its rules, you do so at your own peril. Electricity is going to continue to work. It is going to follow the path, the easiest path it can find, um, and to work within its own parameters and rules. And if we forget about that, we suffer the consequences. So if that scares you a little bit, good. Um, you know, Fear isn't always a bad thing, especially if it's a respect uh, of electricity in particular. So we need to respect the electricity that we're working with, is the bottom line. I don't want you to be scared of it. And truthfully, the more scared you are of electricity, the more likely you are to get injured. So fear it, fearfully respect it, but don't be afraid of it because as long as you follow certain rules and certain habits, you're going to be okay. So, why is it important for us as HVAC technicians to understand how to work safely around electricity? Well, as you no doubt already know, everything that we work with is electrical. everything that we touch, every system, AC, heat, gas, oil, it all is electrically driven and powered. So because of that, we need to learn how to be safe around electrical power. So just as a quick, brief overview before we dive in too much more deeply, um, today we're going to go over what are shocks and burns. We're going to go over arc flash. We're going to talk about Ohm's law, at least as it relates to electrical shocks and burns. We're going to talk about PPE, personal protective equipment to wear around electricity, our tool safety, and then lockout, tagout. One other bullet point that it looks like I forgot to add is wire sizing. So we are going to talk about that, and I'll have to remember to add that back later on. But the thing that I really want to stress is that from day one, you want to work safely around electricity. The only way to work around electricity is safely. I remember back when I taught of course these were younger people, um, and never really saw it as a problem with the girls. Mostly it was the guys, but it certainly could be the girls too. But young people have a tendency to roughhouse a little bit and goof around and push and shove playfully. They don't. Well, sometimes they might mean it maliciously, but usually it's meant in good spirit. Um, so one thing that we want to just always keep in mind is that when we're working with electricity, we want to be serious. We cannot risk getting hurt or having somebody else get hurt because we're goofing around. I think I must have back in trade school yelled at a student at least a couple times a week because they and their buddy are shoving each other and pushing each other and putting each other in headlocks. And it's like, guys, you know, you're going to get hurt. Knock it off. And what would be worse, because even when I was a younger man, goofing around with my friends or roughhousing would be one thing, but if I hurt myself, but I would never want to hurt somebody else. So so just keep in mind a few statistics. Around 300 deaths and 4,000 injuries from electrical accidents occur every year in the workplace. And by the way, this is from the um, National Institutes of Health website, just to give you an idea of how serious it is. So 4,000 injuries and 300 deaths per year in the workplace due to electrical mishaps. Um, electrical accidents rank sixth among all work-related deaths, not just injuries, not dangers, but actual deaths. Um, and in a recent survey by the Electrical Safety Foundation, over a 5-year period, 15% of electrocutions happened while servicing HVACR equipment. So if there are 300 deaths per year, just statistically speaking, so around 45 of those would be while working on HVACR equipment. Kind of puts that into perspective, the importance of working safely every day. Um, if there's going to be something that you're dogmatic about, if you are going to basically be religious about something, be an asshole, even, um, make it about safety. Uh, you know, we should absolutely refuse to work in a situation where we're not 100% safe. Well, 100% is impossible, but at least as safe as possible. Um, the thing of it is that if we focus on safety and put safety first around electricity, there really isn't any danger. Um, the probability of us getting hurt is going to be very, very low, and it may not even be from something electrical. So we all know, or at least should know, if you've taken basic electricity or any other courses or have worked out in the field for any time, um, we know that electricity flows along the path of least resistance. So it basically goes from the source through the load device to ground. Often we think about a circuit as being a positive and negative, a hot and a neutral, but all the neutral really is a path eventually to ground. Electricity, those free electrons ultimately want to end up at ground and then come back to the source in their circuit. Um, their their uh, their their electrons are going to be flowing through what is called a conductor. So these are going to be typically metals like copper or aluminum, offer very little electrical resistance. The free electrons can flow easily through them with little or no hindrance, or otherwise known as resistance. Insulators, on the other hand, are substances which offer high resistance, like to almost infinite resistance to electricity flow. So that'd be like a plastic or rubber coating on a wire. Older wires would use like a fabric, and these are anything that will prevent the flow of electricity is an insulator. Um, so we've all heard not to stand in water around electricity. Why might that be a problem? Well, it's not the water itself that's conductive, but dissolved within the water are, iron, copper, and other conductive materials which will allow current to flow. So, in the same way that a puddle of water is only conductive because of the dissolved minerals within it, your skin and the moisture within your skin isn't inherently conductive. In fact, dry skin itself with no moisture in it would make an excellent insulator. But the moisture in our skin and the dissolved minerals within that moisture. Of course, we all know copper and iron are also dissolved in our blood. So those make our blood and water and sweat extremely conductive. So even a tiny amount of iron or rather, excuse me, sweat or water could actually turn you into a conductor, which may cause you to be able to conduct current to ground. Um, so why does this matter? Well, the reason that it matters is, or rather, a way of illustrating why this matters. It can be understood by understanding Ohm's law. So Ohm's law, in a very broad sense, describes the relationship between voltage, amperage, and resistance, right? So voltage is the potential difference um, from any one point to another point in a circuit. Okay, so when we're measuring voltage, what we're actually measuring is the difference between 2 points in a circuit. So, like say across a switch, if that switch is closed and the switch isn't pitted or corroded, it should measure 0 volts. Why? Because there is no difference. If you're measuring across an open switch, it would be, whatever the line voltage is, say 120, just for the sake of simplicity. So 120 on one side of the line side of the switch. On the load side of the open switch, it would be 0 volts. So that would be a 120 volt difference, and that's why you would get 120 volts across an open switch. Um, Amperage is your flow of your current. So you know the actual, that's what we think a lot of times when we first start learning about electricity is what we're actually thinking about is amperage. But the amperage is actually the flow of the current, the voltage being potential difference. And then of course resistance, which is a negative force that's acting against the flow of current. So it's slowing or even stopping the current. Um, if we think about two rivers, okay, in the bottom of this slide, we see two rivers kind of side by side. One has wide banks. The surface is calm. It's very placid. It looks very peaceful. I would love to be sitting on the side of this river fishing or or camping or something, it looks really, really nice. On the right, there is a rocky shored river with turbulent waters and swirling waves, um, and it's much narrower. So if we think about a circuit, the flow of current through a wide open circuit with no resistance would be much more like the river on the left. It would be smooth with no eddies, no ripples, no waves. Um, where the river on the right is uh, is a circuit with high resistance. All the rocks in the bottom, all the probably sticks and branches, the twists and turns of the shore, that causes a lot of turbulence and resistance to the flow of the water. And in the same way, electrical resistance inhibits the flow of the free electrons through a circuit. So again, what does this have to do with shocks and electrocution? Well, so think about it this way: your skin, bones, blood vessels, the blood itself, that all contains stuff, not just conductors, but then it also has resistive components within it, right? So, as potential difference, or rather, as that current flowing through your body encounters um, encounters barriers, bones, again, skin, organs, it's going to create heat through friction, because current flow encountering resistance um, increases the amperage, amp flow, amp draw, which then increases heat. The potential difference decreases because we've got now a wide open channel on one side of the resistive force, and then we've got this backlog of current on the what would be the source or line side of the resistor, which is again your body. So um, so we are basically creating a almost like a heating element within our bodies. So, so having said this, the reason that low voltage is less likely to cause injury, so like let's say the 24-volt control current on the control side of our HVAC system, is because there's less current flow to create heat. So does it encounter resistance? Yes. Is heat generated when resistance is encountered by that current flow? Of course. But there's less energy available to create enough heat to actually cause injury. That said, can a 24-volt circuit hurt you or kill you? I always say never. Nothing's impossible. So treat that 24-volt circuit just like you would a 440-volt circuit or higher. Treat it with as much respect and as much caution. Um, if nothing else, it's certainly, I have definitely burned out my share of contactor coils or relay coils or thermostats because I created a direct short and smoked a switch or a coil or a wire. Um, so So if there is one indication that there's electrical resistance present, it's a drop in voltage. If you see that your voltage has dropped, then you have resistance present. So that's just one thing to keep in mind. So what is the difference between so what exactly is an electrical shock? I'm sorry. So talking more about the actual injuries that we sustain. Um, Electrical shock is basically the is a severe shock which can cause internal damage and destruction of tissues, nerves, muscles. Um, and the thing about electrical shock is damage may not be evident at first. Just like in an electrical system, you can have like let's say there's a lightning strike near a house, and it might cause a power surge, which affects certain appliances, say refrigerator, oven, furnace, anything with a control board. And for the first year or two, it might be fine. But then after a while, because there's a minor break within one of those circuits within that control board, after a year or two, that control board might fail because eventually, from the heating and cooling and expanding and contracting of the conductors, that control board will no longer be able to conduct current. So, same thing in your body. The damage from an electrical shock might not be apparent at first. The more times you get shocked, the worse the damage gets. Because think about it this way: you are already hurt. So to hurt yourself again, it'd be just like repeated blows to the head. Eventually, it does damage your brain. Um, so if you do get shocked or burned or anything, definitely seek medical attention. There is a tendency within not only our trade or even any trade, there's a tendency for people to just, like, I'll be fine. I just, need to sit down a minute, drink some water, suck it up. I'll be all right. So you want to make sure you get medical attention. If it's something where you feel like you can finish out the day, I mean, I guess that's up to you, but get yourself checked out. And, the bottom line is before, the best way to keep from getting shocked is before you start working on any electrical parts or systems, de-energize the circuit, make sure it's off, and before you work on it, assume there's power. So let me give you a perfect example of where I screwed up one time, okay? So let's say that over here is condenser one, and not many of us remember our first HVAC repair, but boy, do I. Okay, so that's actually disconnect one, condenser one, disconnect two, and condenser two. Really accurate drawings, let me tell you. So a person would normally assume disconnect one is wired to condenser one, disconnect two is wired to condenser two. So I had a no cooling, AC not cooling call. Okay, walk up to the condensing unit, and it's not doing anything. Um, and so, okay, contactor, and contactor's chattering away. Obviously, that's bad. Test the go to, I'm going to go to the extra mile and make sure I test the capacitor. More than likely, it's bad too, but it's definitely worth checking. So, pull this disconnect and start unwiring the capacitor, and got grabbed by the current. I mean, I could not move. I don't know how, but I managed to sort of like just kind of hop my whole body up and down. It's the only way I can describe it. And then dropped the capacitor. Um, but yeah, that was bad. Like I really, it hurt, but it wasn't as much the pain as it was just the fear of being frozen. Like, oh my God, what's um, had I looked, I would have realized that we were crossed. So I wanted to pull this disconnect because this disconnect was the one that was connected to this condenser. So if I had that to do over again, what I would have done was pulled the disconnect, taken out my meter, and then double checked that there was no current coming through the disconnect to the condensing unit. When I, of course, caught my breath and kind of came back to my senses, it really dawned on me that, like, wow, if I'd have taken 2 minutes to verify that there is no power, or had seen that there was power, I might have actually not gotten shocked. Thankfully, I definitely never forgot that and learned from it and never had a repeat of that again. But even if you pulled the disconnect and threw the breaker, make sure that until you verify at the device the power is disconnected, um, just assume that there's always power. Assume it's live. And please, for the love of Pete, do not work on a system that is live intentionally. Um, so that said, if I hadn't been working alone, how might you have helped me break free from that current? How do you help someone who is frozen in a circuit? The um, the answer is you go to the breaker or disconnect and you disconnect power. Um, I think our first instinct would be to tackle them. And now, in that particular case, technically that might have worked, but you can't be sure. If you do that, you might actually get frozen into the circuit with them. So you want to make sure that you disconnect power. There are certain types of insulated poles that are used with high voltage and that you can use to, like, it almost looks like the type of hook that you would use, like a rescue hook you would use in a swimming pool. But you basically just want to disconnect power. At that point, I realize that we want to be fast and help our friends. Well, you need to run your ass to the breaker box. Don't tackle them. Don't try to pull them out. Um, so Another question, you've opened the breaker and pulled the disconnect. Do you need to check power at the unit? Of course, the answer to that is absolutely you do. Please check power at the unit. You don't want to risk hurting yourself because, again, we were cross-connected and didn't realize it. So shocks and burns are the two main types of electrical injury. So again, shocks are more tissue damage or a feeling of like numbness or disorientation. Um, Electrical burns are probably the most common type of electrical injury. I remember once as a kid playing with a cousin of mine, and all of a sudden, outlet in her bedroom arced and was throwing sparks everywhere. Um, and she was like right next to the outlet. She got a bunch of sparks just landed right on her forearm. Um, and the breaker tripped, so we were fine. But of course that hurt. So I took her straight to the bathroom and ran some cold water over her arm, and her skin was a little red, but it was fine. She didn't, that faded. Didn't even really. I don't know if that even counts as a first degree burn or not. But the point is, she wasn't harmed. But we were really lucky because um, sh- sorry, power electrical failures like that can actually result in fires and much worse. So it's a good thing that that breaker tripped. But thermal burns are probably the most common type of electrical burns. In fact, I often joke, if I didn't get cut, burned, or shocked today, did I even show up for work? And I say that tongue in cheek, but um, burns are actually quite avoidable. All of this is avoidable if we're just careful. So a burn is basically thermal contact with skin between hot wires, motors, or other electrical components. So if you've ever encountered a grounded motor or compressor, you know that they can be extremely hot. So um, in fact, a lot of times, like if I come into a house and the blower is locked, it's just not moving. I'll pull the squirrel cage, but I'm gonna let it sit there on usually the basement or crawl space floor for a little bit before I try to pull that motor out because it's gonna be too hot. I'm gonna get burned, and of course, obviously, tools, um, heating element racks and boxes. Um, so the other kind of burn that we can get is an electrical burn. That's when the power is actually traveling through your body. I have a really cool graphic that I apparently failed to put up here, but it almost looks like lightning, or it can look like lightning. Um, it can also look like a little pinprick that's kind of dark colored or black. But basically, that is literally from electricity traveling through your body. Again, hopping from conductor to conductor through your skin cells, blood cells, the minerals in your sweat and in your tissues. You might have a smaller surface wound, but the inside might be what's really messed up. And the thing with electrical burns is they can cause damage to organs, muscles, other tissues within the body. It can actually require a lot of surgery and therapy. Really bad electrical burns can result in a lot of damage. They can really mess you up. And then the other type of burn would be arc flash burns. So an arc is basically a flash or explosion near a person's body due to electrical arcing. We will get into what that is in a moment. But basically, what it amounts to is hot molten metal fragments can be propelled through the air. I mean, think about it like, the contacts on your contactor. If they got so hot that they liquefied and then, you know, vaporized and started flying through the air at you. That's basically what is happening during a arc flash. Um, so obviously, because the metal fragments and whatnot are so hot that they can actually burn your skin and catch your clothing on fire. Um, the the higher power, like in your power plants and around higher voltage machinery, you're going to actually have arc flash suits and special PPE. You definitely want. We'll get into that a little bit later, but that's why we really need to be careful in what we're wearing, because sometimes it may be the burn to our clothes that is actually burning our skin. So, what is an arc flash? An arc flash is a sudden electric discharge that travels through the air between conductors or from the conductor to the ground. Arc flashes can cause third-degree burns, severe injury, and death without even touching you. So that's the thing. You know, if you, a lot of us think of an electrical shock or electrical burn as happening when we've contacted like a bare wire or something, or something's power is somehow traveling through the case of a machine. Maybe a insulator is rubbed off, and so we get shocked by touching the cabinet of a furnace. But you don't even have to touch the a part of the circuit. You can just be standing close enough to where the arc flash can harm you. Arc flashes can cause third-degree burns, severe injury, and death without touching the contactor. And if you think that I repeated myself by accident, no, it was definitely on purpose. It bears repeating. Um, you know, Keep your distance from sources of arc flash. So typically an arc flash is caused by the short circuit or poor electrical contact between contactors. If you've ever pulled if you ever pulled a plug out of an electrical outlet and saw that little bit of a spark, that's an arc flash. If you've ever, especially on a bigger switch, like opened up a switch and saw a little spark, that's an arc flash. Now it's a smaller one, but it is the exact same thing. Here's an example of a much bigger arc flash that happens on a power plant. This is the this is a substation basically shutting down, and as they open those switches, those are the three phases of power. You see that there's a bolt, an arc flash that occurs between the sides of the switch. So this is literally what can happen. That's on a larger scale, and definitely wouldn't want to be standing there. But that is a perfect example of an arc flash. So just because we don't want to go too deeply into this for right now, but it's important for us to understand um, that there are certain types of protective equipment we can wear for our protection. The higher the risk level, which has been usually determined by OSHA, the higher rating of arc flash suits, gloves, and different types of face protection, different types of PPE you should use. The So sometimes on different types of machinery, you will see warning labels like the one on the lower right corner there. Arc flash shock hazard, appropriate PPE required. There should also be some kind of labeling stating the type of PPE that should be used there and the rating, as well as boundary types, warning labels. You basically should have all the information you need right on the outside of the machine. But of course, um, you can also look up with the manufacturer's recommendations and guides. And if you're in a building where, let's say you're in more an industrial type of a setting, your company should have that information as far as what the rating and types of PPE needed to work with a particular machine are. Um, but basically, when working around arc flash equipment or equipment that has a high risk of arc flash, you want to always use the proper tools. Really, that's true for anything. But meters should always be appropriate for the category. Of course, we have lower rated meters for more low voltage, low probability of arc flash or of injury, all the way up to our um, category 4 and 5 multimeters that we use at HVAC. One thing that I like about this particular guy that you see, we have this hoop, so and a removable screen. So the multimeter that I use, I mean, you got to stand there with it, right? And that most of you use. You stand there with it to take your readings. Well, with this, what you can do is actually put this hoop around the conductor and then remove this faceplate and go into the next room or behind a protective barrier so that when you power on the machine, you can get your amp reading without actually being right there. Um, but you can also use non-contact voltage detectors, which are good for, again, a quick little, is this circuit live or not? Um, Infrared thermometers and cameras can help you identify hot spots. So again, when you're pulling that grounded motor out and it is just smoking hot, I mean, even your little infrared thermometer, shoot that at the motor real quick will let you know is it hot or not. Although if you're inside of the cabinet of a furnace, for example, or an air handler, you will probably be able to feel the heat coming off it anyway. Um, but yeah, so remote wireless devices are available to use whenever possible. Um, and then finally, one thing that we always need to use, and I'm um, pretty adamant, is that we wear gloves. Sheet metal cutting, you're probably good about wearing gloves, and most of us are. But if you are working with electricity, you should at least be wearing some of the rubber dip gloves, just to keep yourself safe. If you rub a wire that's live, I mean, it's probably going to bite you, and that might be the worst that you get. But again, those repetitive small injuries can add up over time. So we want to protect ourselves. Over here to the right, you'll see that there are heavier duty gloves that would be used in much higher voltage applications, and even leather over gloves to go over the rubber gloves. Um, when you're when you're thinking about your gloves, you want to always make sure that you are checking for holes, punctures, cuts. Just make sure they're still in good shape, because that is providing a path for electricity to flow. Um, so with the case of anything that we're working on in most residential and commercial HVAC applications, typically we're not going to be working on a live circuit, but we might have to. Definitely wear gloves if you're working with a live circuit. But in some, again, an industrial warehouse, freezer, you might, you might not be able to shut down the circuit. So it might have to stay energized at all times. So, in that case, you would use these super thick gloves. Just bear in mind that the thicker the glove, the higher or rather, the lower the dexterity. You will lose your ability to grip things, but that's where, again, uh, work safely, work as a team, and help each other out. Again, on the clothing thing, we want to make sure that we are wearing flame resistant clothing. We really don't want to wear cotton or natural fibers, or rather, we do want to wear cotton. I'm sorry, stuff that's, but the flame resistant. Not what I'm trying to say is the synthetic fibers, basically the plastic fibers. They melt to your skin and then burn you even worse. Flame resistant clothing also is recommended. If your clothes are contaminated with grease or oil or anything flammable, probably not a good idea to be wearing that to work. And again, it can conduct a flame. It can catch fire and hold a flame and then burn you even worse. So if you're working with certain ratings of equipment, again, higher voltage stuff, make sure you're wearing appropriate clothing for that equipment. The other thing that we don't frequently talk about is our shoes. Well, maybe you do. I've, I guess I don't think about them as much. But you know, good slip resistant work shoes or boots. In certain applications, if they're needed, I don't know many techs, especially in residential, who wear steel toe anymore. But in fact, I know a guy who wears cowboy boots, but he wears good, sturdy cowboy boots with slip-resistant soles. You just want to make sure that your feet are protected and they're holding you up and keeping you stable. So you want to make sure that you're able to stay up, stay safe, stay stable. Um, so other items that you want to make sure you keep on your truck and use, um, eye protection or face protection. Um, you know, on maintenances, I am really good, I will admit, at forgetting my safety glasses in the truck. But if I'm brushing off the fan wheel, I mean, there's dust particles in the air. We should be wearing our eye protection and really even a respirator mask. The little paper ones you wear, like if you're sanding drywall or something at your house. Um, breathing protection. Earplugs. We are around a lot of loud machinery frequently. It's probably not a bad idea to wear earplugs. Um, you want to make sure that your power tools are safe. Um, a lot of us have cordless tools, or yeah, cordless tools now. We want to make sure that we are, not working with a cracked housing or something that's arcing. Um, with a with a brushless motor now, you might not see, with the older brush motors on power tools, you'd often see sparks through the housing as the motor is turning, and that's actually perfectly normal. With the brushless motors, though, if you do see sparks, that means that tool should not be used anymore until it gets either serviced or replaced. Um, but if you are using corded tools, you want to make sure that your cord is grounded. If they're not, you need a adapter. Um, and then check for cracks and again sparks and unusual wear. Just make sure that it's solid. I mean, it might be scuffed up and have some dirt and stained stuff. It doesn't need to look brand new, but as you can see with our drill driver here, we got the frayed cord, we got the cracked housing. I mean, that's not a safe tool really. um, so again, if your tools are in rough shape, repair or replace them as quickly as possible. And really, you just shouldn't be using them. So one thing we want to think about when we're working in an electrical circuit is lockout tagout. So for those of you who are not aware, lockout tagout is a procedure for ensuring that if you have de-energized a circuit, that circuit stays de-energized during the duration of the repair. So you know, it's easy for somebody to walk by, see an open electrical panel, and say, "Oh, why is that breaker off?" and then they, turn it on, and then next thing you know, you're on the roof getting zapped. Um, you want to make sure that you cut power at the circuit breaker before beginning work, but you want to also put and I've got pictures of it here on the next slide, but you want to make sure that other people know you're working on the circuit. So don't assume that others know. Communicate it, but then you're going to put a lock and a tag, and it's going to be obvious that someone is working on a piece of machinery attached to that circuit, so don't mess with it. It's called lockout tagout because you are physically putting a padlock on the circuit and tag with your name on it, the company, the date, reason the breaker is locked out. The information on the tag might be different uh, based on state or local guidelines, along with company policies and procedures. But basically, you're making it very obvious that I am working on this circuit. Do not touch. Um, the thing with lockout tagout is if you are not finished the same day, this provides information on why the circuit is de-energized. Okay, so let's say it's getting on the end of the day, you got to go, but you're going to come back first thing in the morning to work on it. Well, there might be a new shift, there might be new people tomorrow than the people that were here today. So it'd be good if there was something to communicate. Hey, there's work going on here. Um, Especially because you might get held up on the way there. So you might not be able to communicate as clearly to everyone that hey, I'm at work. In larger industrial and commercial facilities, there may be a lockout tagout procedure. Once again, just make sure you're following the company policy. For those of you who are in commercial or commercial equipment, commercial kitchen rather, frequently you would want to talk to the manager of the site, the grocery store, the restaurant, the retail store, whatever, and make sure that you are following their lockout tagout procedure, and make sure that you are signing all logs and communicating the work per procedure. But basically, here's what it, it's not every lockout tagout kit, but there are different ones and different types of components. But this is basically everything that's going to be in most lockout tagout kits. So these are going to be for like your standard breaker. You're going to basically clamp this onto the breaker once it's off, and it's going to basically inhibit anybody from turning the breaker on. Not only are you going to do that, but you're going to put one of these on it, and you're going to put when this claw clamps onto the actual lock, um, you can't open the lock because this is clamped on. But what you're going to do there then is you're going to put a tag saying who I am, what I'm doing, uh, which is going to be fastened to these holes with this padlock. And you are going to be the only one who has this key. And if you notice, there are 6 holes here. So let's say we're on a more complex system on the circuit, and maybe there's multiple of us doing different parts. So as each of us finishes, we take our lock, okay? But the system is still locked out until everyone has removed their lock. So even though, and it's not even in order of importance or like, the supervisor or the manager or something. It's literally any human that is working on this system. If their lock is not there, you cannot physically, or if their lock is there, it has not been removed, I was trying to say, you cannot physically unlock the circuit and thereby potentially injure somebody. Um, and again, so these bigger ones are for bigger switches and breakers. There are all kinds of different. If you've not seen a lockout tagout kit, um, that Google it. There's a lot of different kinds. But basically, it exists so that you can stay safe and be confident in working on the electrical circuit that you're working on. Um, that said, again, we don't want to trust anyone but ourselves that the circuit is de-energized and locked out and tagged out. Unless you have seen it and you have locked it out yourself, do not trust it. If you arrive to the job and I tell you, yeah, it's locked out, we're safe, it's de-energized, go ahead and go to work. You may trust me. You may love me to pieces. You may think that I am God's gift to HVAC. Gosh darn it, I hope you don't think that. That's far from the truth. But you may trust me enough to where you might think, yeah, okay, it's de-energized. I can go to work. Guys, don't trust anybody. You put your eyes on that breaker and you lock it out and you tag it and you make sure that you stay safe, because at the end of the day, you are the only one who has the power to keep yourself safe. Um, so this is just a short video showing kind of, you know, the difference between what happens when we practice lockout tagout properly or not. So this is a little. So that you see this guy's working on this machinery. He's doing some work um, and cleaning it out. The guy who is operating the machine comes back. Why is this shut off? So this is the same scenario, but now our maintenance guy has put the lock and tag on the machine.
Hey, is somebody working on this machine? I'm cleaning back here.
So as we see, it's really a very simple uh, thing to put a tag and a lock on a breaker that keeps us safe. So a buddy of mine, used to be a coworker. Now he's just a buddy, I guess. One time he was a young guy. He was very similar situation, working in an industrial HVAC setting. Was working on a piece of machinery, but he was up high, up in the ceiling. Had the, almost a very similar scenario, had a machine turned off. Well, he had to go finish a repair that had been in progress. It was one of those things where it's like, man, I can get in there in like 5 minutes and get it done. Operator was on break, and of course, it took a little longer than he expected, or the operator came back earlier than planned. Turned on the machine, and this coworker of mine woke up in the hospital. He fell 20 feet to the concrete floor, zapped by 440 volt current. Um, Thing is, this guy also got zapped by 440 one other time. So I don't know. I told him that I think he did actually die. He just is so stubborn he kept coming to work. But all joking aside, had he used lockout tagout, that might not have happened. You think about this: how many old technicians do you know whose bodies are giving them constant pain? They can hardly move. They're moaning and groaning all the time and snapping at everyone because they're in pain and agony constantly. Um, that's kind of what we're going into when it comes to safety. It's not just a bunch of rules. Um, so especially lockout tagout, that's one of those things that we really need to make sure that we're following, because we can't be safe if we can't be sure that the circuit is actually de-energized. So that said, before we work in a circuit and after it's locked out and tagged out, we want to really make sure that it is in fact off. So again, using our properly rated meter for the equipment we're testing, we want to make sure that the circuit is locked out and tagged out. Okay, we're going to test the voltage on a known source of power. So another circuit that we know is energized. Um, we're going to then test our de-energized circuit and verify that we don't have any power flowing. We're going to go back then again and test that known source because we want to make sure that our meter isn't faulty. Um, so, so we want to basically follow this procedure when we're testing a circuit to verify that power is out. Again, back to my condensing unit. Had I followed that procedure, I mean, I wouldn't have had a compelling story to tell today, but I also wouldn't have gotten shocked and wouldn't, know what 220 volts flowing through my arm feels like. Um, It's just, again, we got to follow these procedures and remember safety always. Another device that we can use too is our non-contact voltage tester. So I don't trust it 100%, just mainly because I like to see a zero or a number on the display on my meter. But the non-contact voltage device, or rather, yeah, tester. Basically, it works by picking up um, the EMF field, the electromagnetic field of a circuit. As the current is flowing through the wire, it's creating this magnetic field, and the non-contact voltage tester will pick that up. Most of our multimeters have now a non-contact voltage setting, and again, they'll beep or flash when current's detected. So you want to make sure that the tester rather, is rated for the voltage you're testing. But again, in my mind, I just, if I'm verifying that power is present because I'm troubleshooting, a non-contact voltage tester is fine. But if you're about to start unwiring things and you're checking voltage for the sake of safety, you I would just use my multimeter. Um, so with um, with circuits, we typically have some safety devices that are going to interrupt the flow of current when we are, or rather, when there's an over amperage or over current type of situation, like in the case of a power surge or a grounded motor that's pulling too many amps. Um, so their purpose is to protect the wiring and the load devices on the circuit. How many of you have installed a fuse or a fused link on the low voltage side of an air handler or something because maybe it's older and you've burnt out a a transformer. So now you're putting in a fuse so that if any wires rub or something like that, it'll blow the fuse rather than another transformer. So fuses are basically just a metal strip that's designed to be the weak link in the circuit, um, and it'll basically melt, opening the circuit like a switch, except that it can't be reclosed. It's actually got to be replaced. The thing about a fuse is if a fuse blows, you have damaged the system. So this is why, be leery if you walk into a furnace call or an AC call and you see that, on top of the furnace is a pile of blown fuses. It is the tendency of every new technician to just put a new fuse on and call it fixed. Well, unfortunately, there's a reason that that fuse blew. Um, Usually some kind of a low voltage short. Could be, again, power surge, could be a grounding motor, but either way, the fuse is not blowing because the fuse wore out. The fuses don't wear out. They're designed to blow when there is something wrong. So they indicate a problem. They are not typically, in and of themselves, the problem. So unlike breakers, fuses can't be reset. They have to be replaced. Um, and this was kind of my point, if you have a succession of blown fuses, eventually, just like multiple blows to the head, those tiny injuries will add up. So the system is being damaged, which again is why if you replace um, a transformer on an older system that maybe doesn't have a circuit board with a fuse that's already in it, I usually recommend putting a fused link on that low voltage side because you'll save the system from having to replace the transformer again. So when pulling a fuse, always remember to de-energize the circuit before changing or testing a fuse. Because if you pull the fuse with the system energized, you're going to create an arc flash, which is again more damage. Um, there are several kinds of fuse pullers. It's really ideal to use a fuse puller. Don't use your screwdriver or pliers to pry out a fuse or pull a fuse. That's again more damage. Um, But instead, they actually make these poolers. Now, obviously, with a lot of the modern systems with the control boards, it's easy to just stick your hand in there, pull out the fuse, put in the new one. Technically speaking, you should probably still use a pooler, but I find that, I mean, if it's right there and it's not in, you're not damaging the system, then that's fine. Use your hand, but just consider at least keeping some of these poolers on your truck just in case, because they can be in difficult locations. Um, but definitely never use a screwdriver or a pair of pliers. So with fuses, you always want to use the proper rated fuse. You don't want to use a larger fuse. A lot of One thing that I was taught wrongly when I was new is that you can always go up in rating, just don't go down. And functionally, that will fulfill the purpose. Here's the problem: if you go too high, then if there is overcurrent, you're not protecting the circuit, and you could actually damage a component within the circuit. Usually on the fuse itself is the rating, and so again, if you use too small of a fuse, or if there's an overcurrent type of situation, hopefully that would just be temporary. But if there were, you would actually the fuse would melt, but then current can jump the gap and continue to energize the rest of the circuit. So again, not definitely never a smaller fuse. And if you put a if you put a bigger fuse in, let it only be because you're going around the corner to get the right sized fuse and coming right back. But really, you shouldn't even do that. What you should do is leave the system de-energized and go get the right sized fuse and then come back. So um, just use the right fuse. The final thing I really want to focus on for today, guys, is just wire sizing. So another early repair I did when I was young, I remember it was in property management, and I was working with an older maintenance tech who really, I mean, he's a good guy. He's a smart guy. I'm not trying to talk down about him, but he was definitely one of those guys who was the smartest person that he ever met. Meaning that he probably probably didn't know as much as he thought he did. So we found we had a no cool call on an apartment. Went with him, and you know the indoor blower would turn on, but it wasn't making cool. So we go down to the outdoor condenser, and I take off the mechanical compartment and find that there's a burned up wire. I mean, okay, no problem. So he just finds a random piece of wire that was obviously not the same gauge as the wire that we were, you know, going to replace. So we're going to splice in a new wire. Nowadays, I would have taken that, hopefully, if I could, taken that whole piece of wire from, one end to the other, and with new contactors, new terminal ends, and replace the whole wire. But back then, my fix was replace that burnt piece of wire, which, I mean, it's not terrible. So, but it wasn't the right gauge wire, and he insisted that it was fine. It was slightly smaller, but it was not the right equivalent gauge. So basically, I made a big deal about it, and sure enough, the breaker ended up tripping. Why? Because there was high amp draw, because we were trying to fit uh, more current than that little wire was able to handle. So went back to the shop, found the right gauge wire that matched the gauge on that machine. And now, because the breaker tripped, he was thinking it was a bad compressor. So I went and found the right gauge wire and spliced that in, and it worked. It was just fine. Not that I'm a genius, but it just kind of stands to reason that you want to use, in that situation, you definitely want to pay attention to wire gauges, wire sizing. It matters. It's not just this is the size they had laying around at the factory, there is a calculation that determines the wire size is going. This wire size is going to work for that amperage. Um, so basically, what you want to do, and this really applies not only on repair and service, but especially on installs. You want to really consult your equipment manual for wire sizing recommendations along with applications. So wires are rated for indoor, outdoor, wet and damp. I think there's an underground rating too. And then, so you just want to make sure you're using the right wire in the right application, um, and the right gauge for that piece of equipment. Again, that's generally found in the installation manual on every system. Just did a rooftop unit with my former employer, rooftop commercial condensing unit, and we had to go find four oct gauge wire to use on this rooftop unit. And part of the tricky thing was that where they wanted us to connect, it didn't the 4 gauge wire was like super tight. It did not really fit uh, where they wanted us to connect it. So we really had to like twist the strands really tight to get them to fit. Um, so just make sure that we are following our manufacturer's guidelines for wiring size. Um, Generally speaking, 40 gauge is going to be your smallest, and that's going to be your little tiny like hair thin wires, all the way up to your again oct 4 gauge. That's going to be your biggest. Um, there are wire gauging charts like this wheel that I found online, that can help guide you in what size to use. But again, ask somebody around you if you're ever unsure. Consult and consult your manual. RTFM really does help. So again, I want to thank everybody for joining us today, whether you're here for the live class or you're watching this recording uh, later on. Electrical safety is absolutely vital. We got to make sure that safety is absolutely vital. It is the most important thing that we can do in our careers is to work safely. So, just a few key points to summarize that I want to make sure that we take home with us is ideally, we really want to only work on systems that are de-energized, and you make sure that it's de-energized. Not your neighbor, not your friend, not your coworker. You. You got to make sure you're following all safety rules and recommendations, and especially lockout, tagout. Um, After the power is secured, you want to make sure that you double check the voltage at the unit before beginning your work. There's I am not the only person who thought they properly disconnected power and later found that no, I disconnected the wrong power. This happens, and a little bit of double checking you'll appreciate yourself for doing that in the end. Use appropriate PPE for equipment you're working on. Hey, if your coworkers or trade school classmates or somebody's laughing at you because you look goofy in your safety glasses and your gloves, you know what? You can laugh at them when they've got a bunch of shocks and burns and things. Um, so failure to identify, or rather use, excuse me, safety practices can result in injury and even death. Guys, I don't ever want to hear that one of you who watches this, whether it be today, tomorrow, or 20 years from now, if this video is still out there, I don't want to hear that somebody got hurt. My hope is that you heed this warning uh, every day out there while you're working. Just be safe. Always use the correct size fuse. No exceptions. Don't put too big a one. Don't put a smaller one. Just use the correct one and find the reason that the fuse blew to begin with before you replace the fuse. And When wiring, always use the correct wiring for the equipment and the location per manufacturer's guidelines. And remember, again, electricity doesn't provide you with one free mistake. If you've gotten lucky, then that might have been the last time. So be safe out there, everybody. Keep just crushing it every day. Appreciate everything that you do to make this trade awesome. And we'll see you on the next one. Have a great day. Bye bye for now.